to talk about background field method in hydrodynamics with anomalies, but he didn't say yes here, so I I'll post announcements. And today we have Chris Herzog, who agreed to give us introduction in holographic superconductivity.
Thank you for the opportunity to tell you about some work I did a long time ago, I guess at this point, 2007, 2008. Remember there was a discussion at a workshop I recently attended about, when you ask someone to give a review talk, do you want to have the person, who is on one of the original papers, or do you want to have the person who came much later? And there was some thought that maybe it'd be better to have someone who came much later, because the person, who came to it first, they probably thought some things that were very obvious that weren't, and that's the only way they came up with it in the first place. And so please stop me if you have questions, and tell me if you think some of the things I'm saying are not at all obvious. Okay, so I want to begin with some motivation. And I guess I should probably also give credit to the other people who are on the first papers. Gubser, I think, gets top billing here. He had, to my mind, the first paper that really laid out this model in all its glory. And then I came along a little bit later with two very capable collaborators, Sean Hartnoll and Gary Horowitz. And wrote up a follow-up paper where we filled in some of the physics. And I think after these two papers, there was a lot of follow-up activity for reasons which I'll leave to you whether it was justified or not. So the motivation. Motivation, I guess in a nutshell, is high TC superconductivity. This is, of course, a big problem in theoretical physics today, and the hope is with the holographic superconductor we're going to solve the problem of high TC superconductivity. And of course, we will fail. And as we go along, I'll try to indicate where we fail. So given that motivation, let me begin by reminding you about some facts about high TC superconductivity and what exactly is the problem as I understand it. What people mean when they say, try and solve the problem of high TC superconductivity. So let me begin with this typical phase diagram for the high TC cuprate superconductors. Many of you, I'm sure, have seen this before, but maybe some of you haven't. I don't know. So I've got temperature here on the y-axis, and I've got some kind of doping on the x-axis, something that changes the relative density of electrons in the material. And for the pure compound is actually not so interesting. The doping is 0, say for this lanthanum strontium cuprate or one of the other typical cuprate superconductors. The low temperature undoped phase is an antiferromagnet. So something that has an AL order, something that we learn about in intro statistical physics courses, something that does not really need to be explained. If we keep going over in doping, eventually at low temperatures we see this characteristic superconducting dome. And of course people got very excited about these materials when they were first discovered because the TC was much higher than for previously studied compounds, maybe around 40 Kelvin, and now for other materials you can push that up even above the temperature at which liquid nitrogen becomes a liquid. So you have this characteristic superconducting dome with a rather high TC. And actually, we have a lot of ways of understanding superconductivity. This Landau-Ginzburg paradigm, BCS superconductors. The physics in here is maybe not so mysterious. What people really mean about explaining superconductors is explaining everything else on this phase diagram, I would say. Putting it all together into some model that makes sense from a microscopic picture. So let me fill in the rest here. This is the normal phase. The normal phase is in some sense the most interesting part of a high TC superconductor. These dotted lines are not really supposed to be phase transitions. They're more supposed to be like crossovers. And there are different regimes here, some of which are easier to understand than others. So there's this point of optimal doping where the TC is highest. And we can think about the overdoped regime where people say the normal phase looks an awful lot like a Fermi liquid. What do I mean by a Fermi liquid? I really mean like free electrons where you renormalize the mass of the electron, charge, so forth. But something that looks very weakly interacting in the normal phase. And if you go through the phase transition over here at overdoping, things look familiar. They look, at least according to the experts I've talked to, like, say, a standard BCS phase transition to a superconductor. So maybe this is not the most interesting regime of the high TC superconductors. There's this underdoped regime where the gap, in some sense, in the BCS phase transition, when you form these Cooper pairs, you open up a gap in the energy spectrum. This mass gap persists for T greater than Tc. So there's some sense that the coupling there between the electrons is stronger. It's strong in a way that it's hard to understand using this usual phonon interactions people talk about for BCS phase transitions. Maybe it has something to do with spin physics, given there's an antiferromagnet sitting in the phase diagram. So maybe the Cooper pairs persist over here. I'm not sure this is a settled. Persist at T greater than Tc, and the phase transition has something to do with disordering of the order parameter. And it's sort of hard to understand, what could provide a strong interaction. So this is less well understood, but there's some guesses for what's going on in the pseudo-gap phase.
So why is it called pseudo-gap?
Because the gap closes off. So you have this D-wave order, so it's not an isotropic order parameter, and it closes off in various directions. It's not a true gap. And it closes off, I think, so in the superconducting phase, since it's D-wave order, it closes off at nodal points. But in the pseudo-gap phase, those points broaden a little bit. You still, in many directions, in phase space, gap, I believe. So the region that I guess causes the most cognitive difficulty for theorists is the strange metal phase.
So just
Yeah.
understand the previous. So the pseudo gap means that not the whole gap is surface of the gap. What exactly?
So depending on what direction momentum.
You either have it or not.
So if you can characterize the energy spectrum as a function of momentum of the electron, right? So you say in the x and y directions, the gap closes off, but in some intermediate direction, you still see a gap in the density of states.
Some part of the hemisphere there is a gap. That's what you call pseudo. Yeah?
Strange metal, the strange metal phase. So this has, or non-Fermi liquid. This has non-Fermi, what do I want to say? Non-Fermi liquid-like properties. So what do I mean by that? Let me just give you one example, sort of the easiest physical example to talk about. We can look at the DC resistivity. Make a plot. There's this other famous plot I'm sure many of you have seen. We look at temperature on the x-axis, the resistivity, direct current resistivity on the y-axis. So, below Tc, things a superconductor, there's no resistivity. But above Tc, we have this famous linear rise with temperature of the resistivity. And this is weird. Why is this weird? This is what's expected at high T. For a Fermi gas. Not what's expected at low T. At low temperatures, what do you expect? Well, you can open up from Ashcroft and Merman, or probably many other places where you can see detailed descriptions of this. What do you expect at low temperature for a typical metal? So for a Fermi liquid, you might expect a couple of different terms here. You might expect some constant term that would come from, say, impurities. You might expect some quadratic term that would come from electron-electron scattering. In addition to the lattice, you actually also need the lattice to see some momentum loss here. And maybe you would often also see some interaction with phonons. But there's nothing here that's linear. And it's, if you have some weak coupling model, it's very hard to explain where this linear rise could come from. Again, I was saying this is sort of your expectation at high T, or your sort of scaling expectation if T is the only scale. I recall the Drude formula for you. 1 over rho equals NE squared tau over M. And then, in this model, maybe you could think of, the charge density, the electric charge, and the mass as being roughly constant. So everything here is going to depend on some scattering time. And if the temperature is the dominant scale, or if you're at high temperature where T dominates everything else in the problem, you'd expect that this would go as, say, 1 over the temperature just by dimensional analysis, which would then explain the linear rise in T. But at low T, you've got all these other scales floating around, charge densities, masses, so forth. It's hard to see where this would come from. Okay. So, the problem, again, of what do I want to say? The challenge, right, is to figure out the physics underlying the strange metal and pseudo-gap regions that could also lead to some sort of superconducting phase transitions. That is my understanding of the problem of high TC superconductivity. Explain all the features of this phase diagram, and especially sort of these two and their relation to superconductivity. I probably should have left that phase diagram up for a few more minutes, but so one proposal on the table is for something that's called a quantum phase transition. There are books about this, one by Subir Sachdov. This is a phase transition at T equals 0. It's driven by some external parameter, like a pressure or a doping, what have you, something that's not the temperature. And there's this sort of typical picture people often draw for a system with a quantum phase transition. Again, I'm interested in temperature dependence as well, but here's my coupling. Here's some critical coupling. So this is my external parameter I'm tuning, this G. Maybe it's a pressure, maybe it's a doping, maybe it's something else. And as I go through this line, at that point here, I'm going to have my quantum phase transition between two different ground states of the system. And maybe if you look higher in temperature, maybe it's connected to some ordinary thermal phase transition where there's an ordered phase. And maybe also there should be some sort of crossover regions, right? So that if I just increase the temperature, if I stay at that critical point and increase the temperature, so the temperature is the dominant scale, then there should be some quantum critical region in here that's basically scale invariant where the temperature is the only deformation. The temperature is the only thing in introducing a scale to the system.
Some effects of control filter?
Right. The only operator I'm adding is temperature. So I have some scale invariant QFT. So right, I go through this phase transition. At that phase transition point, well, typically I have some lattice model here, but at that phase transition I get scale invariant. So correlation lengths diverge. I ought to be able to take some continuum limit. I ought to have some continuum description at that point, which is a quantum field theory. Typically the couplings here will be order 1, so it's going to be some strongly interacting quantum field theory. And now, I'm going to go away from that point in temperature. And so here, I should basically just have some quantum field theory that's scale invariant at some finite temperature. So that's a very simple, or a much simpler system, maybe.
I mean, certainly in the case of
sizing model, for example, of critical field, the field is a relevant scaling variable and efficient component.
Yeah, but so
that's actually your horizontal axis.
yeah, so but I want to tune to some point where that external field gets me to a phase transition. At that phase transition, there should be some scale invariance that should emerge. So there should be some quantum field theory that's scale invariant. And then if I go up in temperature, if I stay inside these dotted lines, I can think of as temperature being the only scale in the problem.
So the crossover becomes the second order phase transition? Or?
This crossover is just a crossover. It's not a phase transition.
Okay, but then you're saying...
Oh, at this point. Yeah, I want to imagine this as being the second order.
And how can you say that it will be there? So you have some lattice affected model, and then you see that there is a phase transition?
There are a number of systems which have these simple toy models that have these properties.
Transfer sizing model, where you see non-analytic behavior in preliminary functions.
And you assume that the real materials, they have this behavior at zero temperature?
Well, the point I was going to make is that this phase diagram looks something like the phase diagram I just drew before. So the point is that maybe this quantum critical region I can identify with a big question mark here with the strange metal. Strange metal phase of a high TC superconductor. That's a proposal that's been on the table. It happens to be, for the high TC cuprates, it happens to be buried underneath some superconducting dome. So maybe there's some other parameter that I need to tune. Hopefully I don't need to add too much of that parameter, or I'll destroy this argument that I'm close to some quantum critical point. But maybe underneath that superconducting dome, underneath it in some sense, is buried some quantum critical point. So if you could understand the field theory that describes that quantum critical point, maybe you could also understand the strange metal region of a high TC superconductor. That's a proposal on the table. Let me just write that again. So the underlying quantum critical point should be controlled by some strongly, or at least order 1, interacting scale invariant QFT. I think I said all I need to say. People happy about quantum critical points? So at this point, I want to introduce this notion of gauge gravity duality, or ADSCFT, or holography. It has many different names, which are supposed to indicate varying degrees of generality, ADSCFT being perhaps the most specific. So what is ADSCFT? It's a way of studying a class of strongly interacting scale invariant. Well, it's much more than this, but for the purposes of this talk, it's a way to study a class of strongly interacting scale invariant QFTs. And the way it works is by mapping them to classical gravity. Okay. For the purposes of this talk, that's what ADSCFT is. So I don't know how many people in the audience are experts in this. Probably a number of you are, certainly. I don't need to go through this. But I think for the rest of you, since this is supposed to be an introduction and a review, I'm going to be a little bit slower than I usually am in these kinds of seminars. So there's a basic statement, but I'm also going pretty fast. I mean, if you've never seen this stuff before, this is going to be a little bit mysterious. So there's a basic statement behind the ADSCFT correspondence, which is the following. I can write a generating function for connected correlation functions in my CFT, my conformal field theory. So CFT is a conformal field theory. So we should really have a discussion about what exactly we mean by scale invariance here. I mean, condensed matter people, when they say scale invariance, they let time and space scale in different ways. When I say scale invariant as a high energy theorist, I usually have in mind the conformal group where time and space are also pinned together by the Lorentz group.
This means
Z, yeah.
you are assuming Horowitz and I.
Yeah. So these, in the basic statement of ADSCFT, Z is 1. This dynamical scaling exponent Z is 1.
But the systems have a Fermi set.
Which systems?
The ones you are talking about.
The high TC superconductors have a Fermi surface, definitely, yes.
Yeah. So what about the Z equal 1 and Lorentz and I?
This is definitely an interesting conversation that would, we'll get there in some way, and this is going to be part of the reason what I'm going to show you will fail. There are ADSCFT correspondences where we can break this, but for today's talk, Z is 1. Interesting generalization. So this is what I mean by WCFT, right? I have some collection of operators in my field theory. I'm coupling them to sources. I'm going to compute this expectation value, and this is a generating function for connected correlators of these operators O, right? So the basic statement of ADSCFT is that I can relate this to a partition function of a string theory, basically, strings in anti-de Sitter space, some fixed curved gravitational background, which is going to be a functional of phi naught. Now I have to tell you what phi naught is on the other side of this duality. So the way this works, right, so again, CFT, phi naught sources, my operators O. That should be straightforward from a QFT side. On the ADS side, so anti-de Sitter space, it's some sort of curved geometry. It's basically like a hyperbola with a time-like direction. I'm going to give you another characterization of it, which will be more useful for this talk. So for this guy, phi naught is a boundary value of a bulk field in ADS, D plus 1. So I want D plus 1 dimensional anti-de Sitter space. So the way I think of anti-de Sitter space in this context, there's one very simple way I think about it is the following. Think about it as a half space. So I have some boundary, which is Minkowski space, D minus 1 comma 1 dimensional. So I'm insisting on this Lorentz symmetry here. And then there's a kind of a radial direction here, which goes in. Let's call this radial direction Z, and Z equals 0 over here is a boundary. So I have some fields which live in the bulk of this space, which I'll call phi. And their boundary value is phi naught. Is going to be identified in this correspondence with sources for operators in the conformal field theory. And then there's one further claim. So this is the basic statement. And then there's one further thing I want to claim, which I can't really go into the details here. But the claim is that there exists a large N strong coupling limit. What this means in detail depends really on the details of the field theory. A limit where Z strings is well approximated by low energy limit of string theory, which we know is gravity, and can be evaluated by saddle point. Okay, so you can then, if you can study the gravity theory in this limit, you can compute the on-shell action. You can figure out what this object over here is, this generating function for connected correlation function.
So in general, let's say it's a correspondence between two quantum field theories, right?
In general, yes. Well, quantum gravity, whatever that means. In this case, it's strings and ADS.
One is what you're talking. So what is easier for this purpose to work in this combination?
No, actually, it's worse than that. It corresponds between quantum field theory and quantum string theory.
Yeah.
So it's different.
Yeah, this object in some sense is not really even particularly well defined. You could even think about this as a definition. I mean, that's one very interesting aspect of ADSCFT. You can use the field theory to define what you mean by quantum gravity theory in a particular background.
Okay. So it works much better than the other.
If you could put your field theory on a lattice, yes, maybe you could learn something about quantum gravity. Very interesting direction. Some people are exploring it. For the purposes of today's talk, I'm taking this low energy limit of the string theory where I know it's classical gravity. And this, in some sense, I know better than I know how to study large N strongly coupled field theory. So I'm going to use classical gravity to learn about this object. Where am I in time? This is fine, I think. Okay. All right. So I finally get to the holographic superconductor. I need some basic ingredients. And I need to tell you a little bit more about how this dictionary works. Some of these things are kind of intuitive. All of them could use a more careful derivation that I'm going to give today. But I'm going to try and, I guess, just argue by power of persuasion or something. So on one side, I have operators. On the other side, I have fields, and gravity fields, right? So what operators do I need? What is sort of the minimum set of operators I need to describe superconductivities? Well, I can think about Landau-Ginzburg theory or hydrodynamics or something. Probably I want to know something about energy densities and pressures and so forth. So probably I should include a stress tensor in my set of operators. I want to know something about charge currents and charge densities and how they flow. So I should probably include some kind of, some sort of charge current. And I probably need something like an order parameter, which I'll call script O, that will take on some non-trivial expectation value in the ordered phase. This is sort of, I claim, a minimal set of ingredients to describe superconductivity or even superfluidity. Where are the fermions? It's a very good question. And at this point, there are none. So, trying to figure out a microscopic relation between these composite operators and BCS theory or something is a difficult, maybe even an impossible task. But at the moment, there are no fermions. And this is part of why my story today will fail.
So what is the difference in your terminology between superfluidity and superconductivity? Just
I'll get there in a minute. Ask that again in a couple minutes. So how this works is that this gets sourced by a metric. So I'm going to try and use Greek indices on the boundary and capital Roman indices in the bulk. This gets sourced by a gauge field, a Abelian U1 gauge field in the bulk. And here I have some sort of charged scalar I'll call phi in the bulk. So the minimal ingredients I need to construct this theory, I claim, are these three operators on the field theory side and these three fields on the gravity side.
So it's charged under what? Under the opposite?
Under the gauge field. Oh, you're asking more about, if I had some particular embedding in string theory, what would that charge be? At this point, I'm agnostic. It could be an R-star symmetry. It could be some other baryonic symmetry.
But you mean just the gauge, it's charged under the gauge field A.
It's charged under the gauge field A. Charged in the bulk. Okay, so, and now I'd like to write down some minimal action for gravity that includes these three ingredients. Well, the obvious thing to write down, one of those things that may not be so obvious, is some Einstein term. I need to include a cosmological constant because I want anti-de Sitter space to be a solution. So this lambda is some negative cosmological constant.
So why is it 4x?
Oh, good. Another good question. You can do whatever you want here at this level. One motivation for choosing 4 dimensions is the fact that the cuprates are layered.
Okay.
So the way this works, right, is I have ADS4, which is dual to some field theory in 2,1 space-time dimensions. So I'm modeling a field theory in 2+1 dimensions. So it's layered. Maybe this is a reasonable starting point. If you don't like this, you're free to change it. I mean, yeah, okay. Since I'm recorded, I won't say any more. I need some Maxwell term for F, and some minimal action for the scalar. This is a scalar, again, that's charged under this gauge field. I'm going to allow for some arbitrary potential that respects the U1 symmetry, so it's a function of the modulus of phi. Probably, yeah, I mean, maybe I should, I don't want to really allow for non-singular things, but yeah. Maybe I shouldn't allow the square root of this term. Maybe I should only allow phi star phi. Okay, so, and then D is this covariant derivative, where the charge, I mean, I'm free to shift where I put the charge. Here I put the charge as the coupling of the U1 field. If I had more scalar fields, then I might want to add some parameters here. Okay, so this is what's known, I guess, in the literature as a bottom-up construction. And having proceeded in this way, I've made it totally obscure what the field theory dual is. I've just gone at this from the gravity side. I've figured out what the minimal ingredients I need, and I can't tell you whether this is n equals 4 supersymmetric Yang-Mills or some deformation of it, or what it is. Or it can't even be that, I know, because it's 2+1 dimensions, but some 2+1 dimensional cousin of that. So perhaps, and some people in the literature take this point, you really shouldn't start here. What you should really start is you should start with some string theory motivated ADSCFT correspondence where you know what the field theory is. And that's this embedding in string theory would allow you to fix a number of these free parameters. They'd fix for you the value of the gravitational coupling, the gauge coupling, and this potential. They'd tell you what they are. But for the purposes of today's talk, I'm just going to take this purely phenomenological approach where it's obscure where the fermions are. It's obscure exactly what field theory I'm talking about. Nevertheless, I'm going to be able to say some interesting things. And now to get back to Sasha's problem, there's a small problem here, which I guess if you're an expert here, you've already seen, but let me tell you what it is. So J mu technically is a global symmetry. Why is it a global symmetry? Well, this is a gauge field in the bulk, and the system has a boundary, and so typically, when we write down gauge theories with boundary, we want to freeze gauge transformations on the boundary. We want to prescribe some particular form of the gauge transformation on the boundary. And so it's dual to a global symmetry. The gauge field in the bulk is dual to a global symmetry. So the system I have here is really, to be rigorous, is really a superfluid. It's really a superfluid. The way people have tried to sidestep this in the literature, including myself, is to say, well, just think of this as weakly gauged. And if you think about this U1 as weakly gauged, maybe there's not too much difference between a superfluid and a superconductor. But technically, this model I'm describing describes a superfluid.
So it's not a charged superfluid, which is a superconductor. It's a neutral superfluid, right?
It is a superfluid with a conserved global symmetry, so it has a charge. Maybe you could think of it as the mass of the superfluid.
Sorry, I don't quite understand what difference you make between superfluid and superconductor. What do you mean?
Well, I'm happy if you don't see a difference. But the difference
There is a difference. In superfluids there is a goldstone mode, and in the superconductor there is no.
Right, so here there's a Goldstone mode.
Pardon?
Here there's going to be a Goldstone mode associated with the spontaneously broken symmetry. There's no Higgs mechanism.
Right.
Yeah, this is what I was asking about. That sometimes people just define superconductivity as just charged superfluid, but more precise definition and used in field theory literature is that Higgs mechanism is there and you have dynamical gauge field.
Yes. Yeah.
Okay.
So we better have 3 names instead of 2 because it's confusing.
Sorry, what?
It would better to have 3 different names because
3 different names?
neutral, superfluid, charged, 3 different scenarios really.
Yeah. And superconductor.
So you have no notion of a Meissner effect or vortices or anything like that?
You do have a notion of a Meissner effect, and you do have a notion of vortices.
It has that natural.
The issue is there's no somehow back reaction. So you have these charged things moving around in your system, but they don't produce their own electric and magnetic fields. That coupling is somehow suppressed. But there is a way of studying vortices and Meissner effect.
Would we need to add a tensor field in the box to make gauge field in the boundary, which would make to see?
Would you need to add a what?
A tensor field, two functions, like being
There have been different proposals for how to do this. Some people say that if you just choose different boundary conditions for the bulk gauge field in ADS4, you can get gauging in some sense. I mean, usually I think about, in ADSCFT we say we don't have access to variables that are not gauge invariant, right? So if you were to really make this gauged, in some sense you would then only have access to, you'd have to somehow reformulate this in terms of Wilson loops or something. You couldn't talk about, say, just the expectation value of O alone, because that wouldn't be gauge invariant. So it'd be
backgrounds where you have separated brains, smeared out brains, which actually fix some part of the gauge group.
I haven't thought about it.
Probably break a single, so they probably break a couple more times.
I haven't thought. It seems like it's an important problem, but I don't know any particularly good solutions to it.
Can you motivate for us this choice of action? Because it's phenomenological action, so you want to model some properties of real system, right? So what makes you think that this action is an approximation to strange metal? I mean, what's...
So I can say a few more words here. So this kind of action does indeed come out of certain kinds of string embeddings. You can have charge scalars and gauge fields which come from R symmetries or other kinds of symmetries. And you always have this term as well that gives you the stress tensor. Now, so the strange metal phase, sort of the guess for what it would be, right? I guess it would be, well, so this is going to give you the physics of the superconducting phase transition. And in the normal phase, this is really not going to play much of a role. So it's really this part of the action which would maybe describe the strange metal. You want some way of having a doping, so you need some charge density. And maybe you want to say something about heat transport, so you need a stress tensor. But
Doping would break currents in the right? So
yeah. So that's another issue here. That in this context of this model, by adding the charge density, you are really adding another parameter, which is taking you away from the critical point in this ADSCFT language. And it's just this term alone, which would give you the scalar barrier vacuum state. So that's another issue. Maybe the right thing to do is to try and find a phase transition where you don't have to deform by adding some charge density. And I don't know, the charge density in the cuprates, I thought is, these Fermi surfaces are supposed to have, in some sense, few electrons. Maybe that would be a better place to go. Yeah.
For example, if you look at the spatial function of two currents, do you get, for example, this linear T dependence in the conductivity, things like that, from this model?
Not in this model.
Not this model.
Another sort of damning issue about this model is that you have translation invariance. And so once you introduce a charge density, the charge density couples to momentum. And it's like having a block of charged jello or charged steel or charged gas, right? If you apply an electric field to it, it will accelerate. There's no way for the momentum to relax because of translation invariance. So in order to see that physics, you need some other ingredients. You need disorder or lattice, and that's the directions that people have pursued.
Sure. There is still no dissipation, right? No dissipation, no black hole, no horizons, no anything.
Oh, you can have dissipation. It's just that you can't have momentum dissipation in the absence of. You can have other kinds of dissipation for other kinds of excitations. I mean, there will be a black hole horizon shortly. We'll have some dissipation, but it's the momentum relaxation that's the problem in this model.
What about higher order terms?
High order terms? Yeah, I mean, it's sort of the brilliance from a sociological point of view of this model, right? I've put some few basic ingredients here, and it can be generalized in all kinds of ways, by changing the dimension, by adding higher derivative terms, by adding other operators. And people have tried to do this over the last 4 or 5 years. Yeah. Other questions? All right, so let me try and do something with this model. Yeah, I guess I'm beginning to run out of time here. So let me describe the normal phase, where I'm going to just set this order parameter to 0. Well, it's an order parameter, so in the normal phase it better vanish. And the normal phase I want to think about is a particular solution. It's a charged black hole. Well-known solution, existed for many years. We had nothing to do with inventing it. So I'll give you the line element. So L squared over Z squared minus F dt squared plus dx squared plus dy squared plus dz squared. So the dz, again, is my radial direction. And there's this function f, which is 1 plus alpha q squared. Q is something like the charge of the black hole. So this exists in any dimension. It's just the exponents here, which will change slightly. And so the boundary, again, of my space-time, this deformation of adding a black hole doesn't change the geometry very much close to z equals 0, as you can see from the form of this, that these high-order terms would vanish. And then there's also a horizon, as Ed was asking about. In this case, the way I've written this is z equals zh, conveniently, where f will vanish. I think you can do that in your head. And so the dt squared component of the metric will vanish. And that's sort of a characteristic signature for horizon, at least with these diagonal metrics. So, I leave it to you. This is basically a mechanics problem, right? You write down the equations of motion, which follow from this action. Plug in this data here. I also have to give you the gauge field, q 1 minus z over zh. It's very simple in this case, dt. and it will satisfy the equations of motion. And one other thing I want to point out here, there's a nice limit you can take that will make some of the calculations much simpler. You can also go away from this limit.
This is AZ?
This is AT. Let's just say it. Forget the form notation. Yeah. It's just AT. All the other components are 0. Alpha. Oh, I didn't write down alpha. So alpha is kappa squared ZH squared over 2 E squared L squared, if I've done my algebra right. And so there's a nice probe limit you can take where you can decouple the metric from the rest of the geometry if you want. The so-called probe limit where you take alpha to 0, where the gravitational coupling becomes very weak, like it is, say, in the real world, and you just have this simple gauge field which satisfies a harmonic equation and a ADS spacetime with a black hole in it.
May I ask a small question? Here we have powers 4 and 3, right?
Yeah.
How many horizons do you have?
There's only one visible, I think, in this.
But in total, so
There should be an inner horizon as well, I think. Actually, I guess you can see the inner horizon as well in the coordinate system.
yeah.
I mean, from my point of view, I'm interested in the gauge theory, which lives on the boundary, and so everything behind the first horizon is completely invisible to me. So I don't need to worry about it. Although there are people who've been trying to learn about physics behind the horizon from these ADS instructions. And the field theory should, in some sense, know about it. How it knows about it is a hard question.
Q is the total charge of the hole.
Did I wrote Q? Q, yeah, it's basically related to it's a free parameter. It's basically the total charge in the black hole. And it's bounded. So if you can't make Q arbitrarily large or the temperature will go through 0. So the case where T goes to 0 is known as an extremal black hole. So this is the Hawking temperature of the black hole. You can calculate this in the usual way through surface gravity or periodicity of the time direction. And it's also going to be the temperature of the field theory. Okay, so I wanted to do a simple calculation for you to give you a sense of how these things go. I wanted to show you how to compute the charge density and the charge current. So if I look at A mu, in general, well, in this particular solution, it has a very simple expansion that terminates at order 1 in Z. But in general, for more general kinds of solutions to Einstein's equations, I might get higher order terms here. And this A mu is the source, right? It's the boundary value of this gauge field A. And I was claiming, there's this relation between connected correlation functions and the on-shell gravity action. So the consequence of that statement, that basic statement of ADSCFT, is that if I take a variation of the saddle point approximation of the on-shell gravity action with respect to the boundary value of this field, I should get the charge current in the boundary. So let's see how this works out and what consequences this has for this particular expansion of the gauge field. So for convenience, I'm going to choose a gauge, a radial gauge where AZ is 0. Makes this thing a bit simpler. And I want to look at the variation of the action, what happens to the action when I vary the gauge field. So there are going to be a bunch of terms here, some that come from the scalar, but the pieces I care about come from the kinetic term for the gauge field. So I have d3x dz dividing up the measure into spatial and radial pieces. G z z g mu nu. Oh gosh. dz delta a mu dz a nu. Maybe there's some other terms here. I'm just focusing on the kinetic term. So I'm going to follow my nose, right? I'm going to integrate by parts. So I'll get some piece which is basically the equations of motion for the gauge field, which will be satisfied on shell. So I just discard that, but I'm left with a boundary term here, which looks like what? Well, I don't change the sign. I'm trying to be careful about signs, but I think ultimately I've failed. D3x eta mu nu, delta A mu, dz A nu, plus other terms that I don't really care about for the purposes of this computation. So the bulk term again cancels by the equation of motion. Okay, so I have my expansion. I'm going to plug it in. It's really simple in this case, right? I just have to take a few derivatives and multiply through one derivative. So this is going to become minus 1 over e squared a mu b nu eta mu nu. And so j mu, what is this? It's just minus 1 over e squared b nu eta mu nu. This is just the Minkowski tensor, right? Minus 1, 1, 1, 1, 1. Minus 1, 1, 1, sorry. So the second order term in this expansion can be interpreted as the expectation value of this operator. And this is a fact that's more generally true in ADSCFT. You expand out the fields. There are going to be two Frobenius solutions near z equals 0. The coefficient of the first solution is the source, the leading solution. The coefficient of the subleading solution is the expectation value. Okay, so in particular now I can think about AT as being something like a chemical potential. And I can think about BT as being proportional to a charge density. I can be more careful about factors of proportionality if I want to.
Q is mu, right?
Right, right. So Q in this particular solution, so in general there could be some more complicated solution for AT, but in this particular solution, mu is Q, exactly. And N is basically also Q. No. N is also, JT is also non-zero. It's also proportional to Q. So the chemical potential and charge density are both proportional to Q. So this is a solution, this Reissner-Nordstrom solution in ADS is a solution on the field theory side with both a non-zero chemical potential and a non-zero charge density. All right. So that was the normal phase. I also wanted to say a few things about the condensed phase. I'm going to get sketchier here. At some point, I have to start using a computer to solve the relevant differential equations, and then maybe it doesn't become too illuminating to go through too many details. So let's specialize this potential for the scalar to something that's just a mass term, m squared phi squared. In general, there could be higher order terms. Here it's just a mass. So because of the kinetic term in my action, which I've erased, because of the coupling to AT, I'm basically going to have some effective mass, which is the mass I introduced by hand, plus a correction that looks like GTT AT squared. And if I plug in the formula for the Reissner-Nordstrom black hole that I just erased, what is this? This is, well, GTT is negative, right? My convention for the metric. So I've got minus z squared over f, q squared over L squared, 1 minus z over zh squared. So there's that q corresponding to the charge of the black hole. So what do you take from this? You take, if I tune up q large enough, this effective mass is going to go negative. Where does this come from? So remember, I have some gauge kinetic term for the scalar field. So there's a connection to the gauge field, and I look at the time component of this. It has this form.
Is it easy to make a connection with the original Landau-Ginzburg type of energy function? Because you had it recorded.
So in the bulk, it's rather interesting. So in the bulk, you would have said in the Landau-Ginzburg paradigm, I should like introduce a negative mass, and then I should introduce some positive quartic term to stabilize it. And here I haven't done that. I've introduced some mass that's stable initially, and then by tuning up the charge density, I'm introducing this instability. And you'd ask, well, how come it doesn't just run away? And one interesting thing that happens in the bulk here is if you look at what happens, so in general, mf squared will be less than or equal to m squared, and it will go to m squared at the boundaries, at z equals 0 and zh. So at z equals 0, this vanishes, and z equals zh, this vanishes, and, well, this also vanishes, but if you take the limits right, you'll see that this whole term vanishes at the boundary on the horizon. So it's sort of stabilized by the boundary conditions. So you don't need to add any more to the potential here to get this physics of a superconducting phase transition. There's a slightly different question you could ask. So this is on the bulk side. You could ask, is there some interpretation on the field theory side as a Landau-Ginzburg model with phi to the fourth and higher couplings? And I think the answer to that is yes, there is, although it's somewhat involved to deduce it from this construction. OK, so
What if it becomes negative, this m squared? If you have condensate of phi inside of your bulk?
That's right, that's right. So what will happen is you basically, another way of thinking about this is pair production. So you have this scalar particle which has a charge and a mass. You increase the charge of the black hole enough, it will repel, well, the gravitational attraction will be insufficient to keep the particles bound to the black hole, and they'll eject these scalar fields into the bulk. But then they can't make it to the boundary, basically because this mass goes back to m squared. Or because you can think about it also in terms of the potential well they experience in ADS. And so they condense in some cloud outside the horizon.
Below the Friedman.
They go basically below the B. Yeah, so there's this additional wrinkle that in ADS m squared is allowed to be a little bit negative to begin with. But there is a BF bound below which it can't go without going unstable. And what you really need is for this to go below the BF bound. Other questions? I'm officially out of time. I guess how long should I keep going? It's open.
We'll try to wrap up, but if you don't rush.
Okay. I'll give you some highlights. Okay, so I hope I've convinced you there's a phase transition here. So let me draw some pictures. So to actually find the solution, I think you need numerics. At least I couldn't find a nice solution to these nonlinear set of coupled ODEs. So there's a numerical solution from which, similar to the way I calculated the expectation value of the charge density, you can calculate an expectation value for the scalar field. So let's do it for some scalar field of conformal dimension 2. And I want to plot the expectation value versus temperature. And the way this plot looks, something like this, roughly, in the probe limit for the experts. So TC, basically by scaling, has to go as the square root of the charge density or as the chemical potential, depending on whether you want to work in grand canonical or canonical ensemble. The phase transition is second order. With some standard Landau-Ginzburg mean field scaling exponent near TC. So I guess this is sort of another reason why we failed today to say too much about the Coop rates, right? We've kind of focused on the superconducting phase transition. We haven't said too much about the normal phase. And everything about the superconducting phase transition is perhaps much better or much more simply explained in the context of Landau-Ginzburg's effective field theory. This is a mean field phase transition. There are a few interesting things that come up. One is that, at least for this particular set of parameters that I've chosen, there's a large gap. We can argue about how natural this set of parameters is. A large gap. So I want to think about the gap as being the expectation value of this scalar with dimension delta raised to some 1 over delta power to keep the dimensions right. So you can look at what happens for BCS, which is basically weak coupling, where twice the gap has this well-known form of 3.54 TC. You can study high TC superconductors, where this is about 4 to 7, maybe, times TC, so much larger. So this gap is a measure of the coupling strength. We can think about what happened in this model for this particular set of parameters. Well, this number here is basically this 8, right, where this goes at low temperature. So here we have about 8 TC for delta equals 2. Of course, this number is going to depend on delta and other things like the potential I put in for the scalar and so forth. But as naive choice or natural choice of parameters, you get a large gap, which says something about, despite the fact that I'm satisfying some Landau-Ginzburg mean field theory, that I'm getting strong coupling physics underneath it.
But your definition of the gap is a bit arbitrary, right?
What's a bit arbitrary?
The definition of the gap.
No. Let me get back to that. Yeah. Let me try to make that more precise. That's a good point. So how do I want to define this gap? Let's think about the conductivity. So there are lots of nice things you can do within the context of this model. I'm going to show you one. There are other things we can do, like think about Meissner effect and so forth, vortices. So the conductivity, what I want to do is I want to do an experiment where I apply an electric field and measure the charge current. In the context of gravity, what I'm really going to do is I'm going to look at small fluctuations. I'm looking at linear response of some field AX, which I'm going to assume has a time dependence I omega t and no spatial dependence. So a homogeneous electric field. So the electric field right is going to scale as AX times I omega, right? So if I look at the equation of motion satisfied by small fluctuations of AX in the superconducting background, it satisfies some second order ordinary differential equation, which again, in general, I'm going to have to solve numerically. I had a nice analytic way of solving it in a particular limit, but I think in view of the time, I'm not going to give it today. So again, this was in the probe limit. To make things a bit simpler. In general, if I go away from the probe limit, I'm also going to have to consider couplings to the metric, because charge current couples to momentum. Momentum is described by the stress tensor. The stress tensor couples to the metric. And I'm going to look at a near boundary expansion of AX. So again, the leading value is the source, which in this case is the electric field. EX over I omega, if I've gotten my signs right. And then there's a term that describes the second order. The next guy is the expectation value, which in this case is the current in the x direction. And if I want the conductivity, well, I've got to solve for AX, look at some small z expansion, and take the ratio of the current in the electric field by Ohm's law, right? Electric field times the conductivity is the current. So, yeah, in general, we need numerics. If I had 5 more minutes, I would show you some analytic approximation of what goes on. As it's not, let me just tell you what happens. So in the probe limit, if we look at t greater than tc, where we don't couple to momentum, we're going to get a finite conductivity. And sigma xx winds up just being a constant, 1 over e squared. for all frequency. And then below TC, let me draw you a picture of what happens. It looks something like this. So here's the value. This dotted line would be the value of the real part of the conductivity in the case where we're above TC. And then if we look at, say, t equals 0, the real part would be a curve that looks roughly like this, which has something like a gap. I guess it doesn't quite go to 0. It's not a true gap, I think, in some sense. This would be the imaginary part of sigma xx at t equals 0. So you solve these things numerically. This is what you find for the conductivity. And this here, we do it for a scalar of dimension 1. This is basically sitting there at 0.1. This is the frequency. So this is my argument for why I can think of this guy as the gap, because it's sitting there, in this plot of the conductivity is, the region where you start to get some non-trivial response to an electric field, or you start to get some dissipation to an electric field. So there's also this imaginary part of the conductivity, and if you think about Kramer's Kronig,
Conductor, there is the delta function.
Right. So this guy is basically going to scale as 1 over the frequency at small frequency, and it implies basically by Kramer's Kronig that we're not going to see this numerically, but by analyticity there has to be also some delta function sitting here at 0 frequency, which is giving you the infinite DC conductivity of a superconductor. In general, there's this more complicated story. If we're away from the probe limit where we couple to momentum, then there'd be 2 contributions to this delta function, one from translation invariance and one from the superconducting order. But in this probe limit, this is purely from the superconducting order. So this is a classic textbook plot. I was very happy with this when I saw it 5 or 6 years ago. You can open up, for example, Michael Tinkham's book, and there's a classic textbook plot of the conductivity, which has exactly these features for the imaginary and real part of the conductivity.
Of course, high temperature superconductors have D wave, so there is no gap.
Right. So this is an S wave superconductor. The high TC cuprates are D wave. They have D wave order. That's another failing of our model. Another reason why we failed today. And yeah, for the D wave, I guess you see a gap in certain directions and not in others, right? Depending on which way you apply the electric field. It's more complicated than that.
So it's there is no dependence on the direction of the. This is a gap for quasi-particle. It's a isotropic for momentum space for quasi-particles, but not for currents.
I see. Yeah, that's interesting then, because in these models, if you were to put in, say, P wave order or D wave order, you would see in the conductivity, you'd see gaps in certain directions and not in others.
This probably means that there is a problem with identification.
There's still dissipation below TC in the cuprates.
Yes.
So that you don't have a persistent current.
Okay, so, but maybe I can't say too much about cuprates, but somehow from the string theory model, the message I'd like to leave you with is that we've able to reproduce classic low temperature, classic results for S-wave ordinary superconductors in this Landau-Ginzburg part.
Does your temperature dependence of your order parameter follow the BCS model roughly? Like if you're just plot them on top of each other, or is there significant deviations?
I think it's rather, well, it really depends on the details of the model. I mean, near TC, you get this Landau-Ginzburg result. But you want to know if I go further, I think I could probably cook up a model where I get arbitrarily good agreement, but generically, no. Yeah, there's, I mean, if I, for example, if I were to look at the case of O1, this thing actually diverges at low temperature, and the probe limit is probably quite different.
Yeah. Chris, when you're saying cook up models, so what do you actually modify in the original?
Right. So, well, I mean, one obvious thing you can do. So I chose this potential to be m phi star, and then there's some relation that something like m squared times the radius of ADS is delta times delta minus 3, radius 4. So if I'm looking at delta equals 1 and 2, then there's some corresponding m squared, which I took m squared r squared to be something like minus 2, I think, today, to get delta equals 1 and 2. But one obvious thing you could do is play with the scaling dimension of the order parameter and see if that changes anything. Or you could add higher order terms here. Or you could add couplings, stranger couplings of the gauge field to the scalar, or you could add higher curvature terms to the metric. There's just this, it's both a feature and I mean, from a sociological point, it's a feature for me because it means there are all these people now who write papers where they change something small and try and publish it. From a larger scientific point of view, it might be something of a bug where you don't really know what the rules of the game are, and it's a little bit too flexible.
In the holographic model to realistic model, what do you compare as an input, like critical exponents or something?
The critical exponents are very difficult to change. They basically are fixed to be Landau-Ginzburg mean field.
Even if you change your background or content?
Yeah, I think you could maybe try to include 1 over n effects in gravity. That might start to change critical exponents. Of course, that's a hard problem because now you're moving into the realm of quantum gravity.
I mean, from a philosophical point of view, right? So you should first have some input to fit your holographic model, then get some non-trivial result, right? So my question is, what is the input and what is the non-trivial result?
I mean, one thing to do is just to see how generic these predictions are, regardless of the input parameters. Another thing to do is to try and look for particular ADSCFT duals. There's some sort of stringy models that will fix these things like potentials and so forth. And another thing to do is to try and build more features into the model that make it more realistic from a phenomenological point of view, like seeing what fermions would do, or trying to put in a lattice. Here I had translation symmetry breaking. One way of fixing that is to break translation invariance through dirt or through a lattice. And so all these games people are playing.
You said that embeddings in string theory will allow you to fix some relations between parameters. Do they have many of these relations in terms of superconductors?
It's hard for me to say. I feel like I'm sort of running up into the string theory landscape problem in a different way. There are
sort of too many ways to.
I think there may be just too many ways. Although at the same time, it's very hard even to construct a single way because of this issue of consistent truncations. I mean, string theories have infinite numbers of operators and fields, and to write down this simple gravity model with 3 operators in it, I've made some rather brutal truncation of a full string theory. String theory lived in 5 more to 6 more dimensions, and I'm just taking a few of the degrees of freedom. And there's an issue, right? If I reduce the temperature here at some non-zero chemical potential, the chemical potential looks an awful lot like a negative mass for charged fields. And so if there's anything else that's charged in your string theory, the first problem you have to face is, what condenses first? And once one thing condenses, do other things condense? What fields do you keep? What's the relevant physics in the string theory to keep? And that's quite a hard problem.
Is it possible to include fermions with this?
Yes, yes, and there have been a number of very interesting papers where people have tried to introduce fermions in one way or another. One is you just write down it, you add the Dirac Lagrangian to this gravity model. Another way is to think about the gravity model coupling to some stress tensor, where the stress tensor has an equation of state that's characteristic of fermions. So there's some very interesting papers that have come out of this.
You think about bulk fermions, and you probably ask about boundary theories.
So a bulk fermion should have some fermionic operator dual. Yeah.
But the bulk theory is not, in this case, is not really a gauge theory. Okay? There is some field which can flow and it has dissipation, etc., but it doesn't really has a charge, right? It has a charge in the sense that there is density and mu, and it can flow, but it is not. It's not a gauge theory, right?
In the bulk, it's definitely a gauge theory.
On the bulk, yeah, but on the boundary.
On the boundary, I think.
The physical system. Boundary, because at the end we study some physical system, right?
In the boundary, it's, I think, more rigorously thought of as some sort of superfluid with a conserved charge.
But, for example, vortices would be like in helium and not like in superconductor.
Yes, so. Although people have played these weird games with the boundary conditions for the gauge field, and they've tried to argue that they can, at least in the ADS4 context, write vortices that look more like superconducting vortices.
So I guess one of the achievements of this model from what we're emphasizing is that the gap is a large multiplicative factor times TC, 8 times TC. And I guess you're saying that's a reasonably robust result? Or, I mean, you said it could be varied. How much could it be varied depending on inputs?
Oh, well, for O1 it goes up to infinity. So it's rather sensitive, I think, to the input parameters. And I think you could probably tune it away if you had a mind to.
Let's do that, because that's a nice result to sort of hang on to if it's robust.
You said a moment ago you can have more than one thing condensed and maybe in different orders, and that's actually a really positive thing for the recuperates, where there's the suspicion that there may be multiple order parameters computing, and you have some hierarchy of energy scales and temperatures.
Mm-hmm.
You can turn on a magnetic field and suppress one and open up another. Has anybody explored that possibility, how these other things might interact with the superconductor?
Yes, yes. I mean, the simplest thing to do is to add another charge scalar. See what happens. You could add some interaction between them to see if you get phase separation or not. There's been a handful of papers about this.
The problem is that there are other parameters which might be condensed non-zero momentum.
Non-zero momentum?
Yeah. A charge-based one.
Yeah. You could also try to look for charge density waves. People have done a little bit of that too, yeah.
Mm-hmm. Also, so there is a charge black hole, and there is this whole issue that you can go to t equals 0 limit and you still have a horizon, right? At t equals 0 you still have entropy of the system, so it is very... So if you have strange metal don't exist at t equals 0, right? So we cannot even ask whether it has entropy or not.
Yeah, so there have been various approaches to this issue. There have been papers written about the fact that the Reisner-Nordstrom black hole has non-zero entropy at zero temperature, and given a name to these kinds of liquids, semi-local quantum liquids, I guess. There are papers by Honglu and friends.
I'm simply asking if we have any hints about strange metal that they have something like that. That they could have entropy at zero temperature or something. But
I think this is
the ground state is multiply degenerate or something like this.
And I think this is a rather weird feature of this
it's
model.
Very weird, but maybe realize it, maybe not. Yes.
Another thing you can do is just take a different gravity solution which has a black hole, charged black hole, which has zero entropy at zero temperature.
Okay.
A way to do that is to add.
What empirical information tell you.
Such solutions exist.
Yes, yes.
What should we do to make the entropy of black hole zero?
Well, the simplest thing I know to do, so one way of thinking about this charged black hole with a abelian scalar, okay, so if I start with an ADSCFT, how do I want to say this in the simplest way possible? There's this R symmetry that occurs in a number of these ADSCFT duals. It typically is some big non-abelian symmetry group like SO8 or SO6 for the maximally supersymmetric H series. So what people often do is they make what's known as some consistent truncation to the U1 subgroups inside these. So like SO6 would have, I don't know, U1 cross U1. So we might have 3 U1s. And so you write down a model which has 3 gauge fields and some extra neutral scalars, which is a consistent truncation of these ADSCFT constructions. And by deciding what chemical potentials to turn on, I think you'd have, I think the minimal way to do this is to have 2 U1s. You come somehow pinned together to have the same chemical potential. And there's some neutral scalars in addition, and this will have a black hole solution which has 0 entropy at 0 temperature.
This is very interesting as a microplastic because this non-abelian fields may correspond to some of these other parameters in the boundary problem.
There's a recent paper by Zonin, Stalm, and Davison where they used this particular black hole and tried to argue they could get linear DC resistivity and temperature.
So it's a black hole with 3 U1 charges?
I think it actually starts with 4, and they look at, there's some subset of 2 which produces this black hole.
Because I thought that SO6 says U4 and U1 cube, and you can have like a CU1 or something like that.
This is ADS4 cross.
This is different, yeah. But still, what is the group then?
SO6?
In SO8. Yeah, I have to refresh my memory. I thought it was 2, 3, and 4, the number of U1 groups for S4, S5, and S7.
Okay, I suggest to send Chris.